Okay, so let's move on to momentum. Momentum, there's more stuff going on. So we'll have to go through and kind of keep track of everything. So first, again, I'm going to say momentum, this control volume has width dx and height dy. And what I want to do is now we'll take an inventory of all the stuff that's going to go in and out of this in terms of momentum. So first of all, maybe it helps to remember that momentum is computed using velocity times mass. Right? So we need to find all the things that are related to that. Maybe before we do that, let's actually write out what our most general representation of conservation of momentum is. So we're going to say momentum in is equal to momentum out plus momentum stored. Some of you may have a problem with this, though. What are we missing from this balance? Not quite. So what's missing from this is the fact that if you have some fluid that's coming in and decelerating, what has to happen to that, to the entire body, right? Yeah, I mean, so you have a force. You have forces that have to balance the change in momentum. Right? So this is not complete. We have to say there's some sum of forces that have to add and balance all the momentum that's occurring here. Or think about that. Like if you have a lot of fluid that comes into a tub or something, and it's going from having velocity to not having velocity, that tub is going to start moving, or there's a force that has to be pushed back against that change in momentum. So okay, this is all good. So this is kind of complete. But what we need to do is think about, actually, we want momentum in a particular direction to be conserved. So all of this has to be true for, let's say, the direction x. So this would be x momentum, x momentum, x momentum. This entire process has to be repeated for every dimension. X momentum, y momentum, z momentum if you have it. By the way, in this, in this problem, we're assuming that there's no flow into and out of the page, so it's a two-dimensional analysis. Okay, so with that, let's go through and start doing the inventory of stuff that is going on here. So we'll start from the left. What do we have coming in? We're going to have, again, we're thinking just about the x component here. So we have the velocity times the mass. So velocity is going to be u. And then what's the mass flow rate going in? Well, that is also related to the velocity. It's u times rho times w times dy. All of that evaluated at x. So effectively, u squared rho w dy is what my momentum, my x momentum going in from the left side is. Okay, on the right side, we're going to have, again, that same thing coming out. I'm just going to be a little bit lazy, and so instead of writing this plus the differential again, I'm just going to write, so assume that this is the same thing, plus the differential, so it'd be plus the differential with respect to x of u squared rho w dy times dx. Right, hopefully that makes sense. So this would also appear over here. So that's the x momentum in the x direction. What about momentum in this y direction? Again, remember we're thinking about this is an x momentum conservation, but there could be fluid coming in, fluid can be coming in like this. So there could be some y momentum that's occurring. But let's think about what is the x component of momentum as it relates to y velocity. So that actually ends up being u, the x velocity, times v, the y velocity, times rho w dx evaluated at y. So it's the y component of the x momentum. right? It's kind of hard to think about. On the other side, you have the same thing, but plus the differential. So that's going to be d dy of u v rho w dx times dy. Okay, so we have all of our momentum, as it's kind of the most straightforward part of momentum, stuff that's coming in due to mass transport. But there's other stuff that we have to think about, right? We also have to think about all the forces that are involved. We have to think about momentum storage. So let's look first at momentum storage. That would be what? Pick a different color. So let's go with green for, oh no, I used pink last time. Pink for storage, okay. So pink for storage is going to be partial with respect to time, w dx dy, that's the volume, times rho, so that gives us our mass, times u, right? And u is our x component that we care about, or the x velocity that we care about. If we're doing this for y, this would become, that thing, but with v in the balance. So that's stored. What else do we need? So let's also think about the forces now. So if I have forces, if I have fluid coming in like this, it's possible, I have a boundary down here, it's possible that the velocity is going to be affected such that there's a velocity profile. If there's a velocity profile, then you have fluid sort of shearing over itself. And that introduces forces. So you're going to have a shear force on this surface. You're going to have a shear force on this surface. That's maybe fairly straightforward if you think about fluid moving this way. But you also have shear forces as you're sort of sliding over itself. There's a force on this boundary kind of pulling and this boundary kind of pushing. So you have forces on all four faces related to shearing of the fluid. So let's do an inventory of those things. I'm going to use orange here. So in this direction, I'm going to just kind of draw it anyway, but in this direction, it would be the shear on the y plane in the x direction, multiplied by the area, which is w times dx, evaluated at y. And then on the other face, or the opposite face, I just draw it in the opposite direction. And it would be the same thing, but plus the derivative. So that would be partial with respect to y of tau yx w dx times dy. Those are the shear terms there. Then on these faces, instead of it being tau, it's sort of a normal shearing, and so that becomes sigma. So we write that as, let's see, this way. So it'd be sigma in the x direction on the x face times dy w at x, and then on the other side we'll draw it like this. So it's the same thing plus partial with respect to x of that, so sigma xx dy w times dx. Okay, so shear forces are taken care of. What other forces are going to act on this control volume? Any other ideas? Pressure. Yes, thank you. Pressure is going to act on this. So we'd have on the left side P times the area dy w. And then on the right side, the same thing, plus the derivative in x, P dy w dx. One more thing. Force, one more force that acts on everything. Gravity. Okay. Very good. We haven't forgotten about gravity. So gravity is going to be w dx dy, our volume, times our density, times the gravity component in the x direction. Always remember, we're doing this in the x direction. So we'll do the same thing in y, but you want to capture just the gravity component in the x direction here. Okay. There's a lot of stuff here, right? But you're just kind of going through and doing an inventory of everything that is involved, and then we have to go and write out the equations. What you'll notice is, the way I've written it, all this stuff that sort of is duplicated, this will cancel with this term, this will cancel with this term, and so on. So we could do that real quick. We could say this cancels, this cancels, this cancels, this. And so these little guys cancel here, right? Once we've done that and we realize all these equations have to be added up, we can look at stuff that's common, right? So again, we have our W term is appearing in every term. So that can cancel. dx and dy can cancel because they're constants. And so when we actually go to write this out, we would get the following equation. So we divide everything by w dx and dy, and writing it out becomes this simplified version. So we have to be careful that we're capturing this sign. You have to take my word that we're doing it right because you can't see it. But we have to be careful we're capturing this sign. And the way to capture the sign would be if I drew positive x, that's going to be a positive to start. And then if it's in, then it would remain positive. I've drawn this in the negative direction. So this is coming in, but it's negative x. So this is a negative term, and so on. So keeping that in mind, we're going to go through. The first pressure term becomes partial of pressure with respect to x. And then we have a partial of sigma x with respect to x plus the partial of tau yx with respect to y. We have our gravity term, which is rho times gx. And then on the right-hand side, that equals, we'll pull the density out for everything, and it's just density times a bunch of stuff, which is partial of u squared with respect to x plus partial of u times v with respect to y plus partial of u with respect to time. Hopefully that's right. OK, so this is interesting. I guess it's a step in the right direction. But if you look at this, we don't really know much about sigma, and we don't know much about tau. So what we want to do is substitute in equations that help us get rid of those kind of unknown or ambiguous quantities. We can do that with the rate equations we derived or could derive. So those would be tau yx is equal to mu times partial u with respect to y plus partial v with respect to x. So that's the rate equation for shear stress. And then sigma xx is 2 times mu times partial u with respect to x. So I didn't tell you where these came from, but you can go look these up. It's sort of the definition of these terms. So we use this. Let's substitute this into the top equation. And once we do that, there's some algebra we're not going to go through. But if you do that, you end up with the Navier-Stokes equation. So we'll just write that out. Navier-Stokes, this is what? X momentum. That is minus partial p with respect to x plus mu times second derivative of u with respect to x plus second derivative of u with respect to y plus the gravity term rho times gx equals the same stuff on the right hand. So it's rho times u times partial u with respect to x plus v partial u with respect to y plus partial u with respect to t. OK. My hand is cramping. So this is Navier-Stokes. Or you go to a fluids textbook, you go to the heat transfer textbook, this will appear. It should appear. This is a complicated equation, right? This is just one component. You do the same thing for the y direction, and you get a similar result. And actually, I probably should write that out just so you have it. We'll do that quickly. Partial p with respect to y, mu, second derivative of v with respect to x, plus second derivative of v with respect to y, plus rho gy is equal to rho. Now it's u times partial v with respect to x, plus v times partial v with respect to y, plus dv dt. Apologize, my u's and v's look a little similar, but yeah. So you can see it's a really similar equation, right? But you just have a few key differences. You're looking at pressure gradients in y. That makes sense, right? You're looking at how the v component of velocity interacts. So this set of equations is, like I said, complicated. How do we then go about simplifying this down to make it useful for our boundary layer applications? Right, we'll get to that. I guess we'll get to that next time. But in the remaining time here, let's go through something that's actually relevant for heat transfer. So this is all like friction factor stuff. There's no energy in these terms. So let's go through the energy balance and get that out of the way. And then I think that'll kind of wrap up for today.